Okay, so let's continue with our connection between random matrices and free probability theory. So last time we looked on one random matrix, because I mean there you can see that in the limit you get a semicircle, and we were in the course of proving this. So last time we calculated the moments of a Gaussian unitary random matrix for arbitrary n. And so just recall. So A is a GOE n, so this means it's an n by n matrix where the entries are chosen in a random way, and the entries are chosen as Gaussian complex random variables which are independent up to the symmetry condition. Now, of course, the A should be self-adjoint, so I have some symmetry above about the entries above and below the diagonal, but otherwise they should be independent. And of course, our state, with respect to which we calculate everything, is the trace tensor the expectation. So we take the trace of our matrix, sum of the diagonals, this is a random variable, and of this we take the expectation. Okay, we saw last time, if I calculate the mth moment of our matrix with respect to this, then we get a very nice and precise formula, which is very much like our moment cumulant formulas or things like this. So it's given by summing over pairings, all pairings. I mean, we are not yet in the free probability world, so I mean, generally we have to sum over all pairings, but then the pairings make a contribution which depends on n. N is the size of the matrix, and the contribution is n to the number of cycles of gamma phi minus 1 minus m over 2. Okay, what is this? Here, pi is a pairing, but here we consider pi as a permutation by just declaring the blocks of our pairing as the cycles of the permutation, and then gamma is another permutation, a fixed one, namely the permutation which just moves every element to the next element. I'm just adding one, but in a cyclic way, not n. Okay, then gamma pi is an element in the permutation group of m elements, and here I take the number of cycles. Okay, good. Yeah, so that was our formula. And now, of course, this is very complicated. I mean, if m is large, there are many partitions, many pairings, and I mean, I will have here a lot of different contributions in n. I have a precise formula, but of course, it's not so easy to sum this completely. But if n goes to infinity, then of course, only the leading order term where this is the largest will survive. And of course, the biggest contribution here should be 0, otherwise it would explode. If it would be less than 0, then it would go to 0. If there would be something bigger than 0, it would go to infinity. So of course, the normalization in our random matrix is chosen in such a way that the leading order for this guy will be 0. And everything else will be less than 0. This means it will go to 0. Okay, and then last time I also showed you that, of course, I mean the leading order term is 0 exactly for the guys which are non-crossing. And this, of course, makes the connection with our free probability theory, because then we are just getting the formula for the moments of a semicircle. Okay, so maybe let me also maybe recall when I gave you the idea of the proof last time. So namely this leading order, this exponent of n, the number of cycles of gamma pi minus 1 minus m over 2, this is always less or equal to 0. And of course the whole thing only makes sense if m is an even number, because otherwise there are no pairings. So in particular, this formula tells us that all the odd moments are always 0. If m is even, then of course this here is a natural number. I mean m over 2, or an integer number. So this is an integer number, but it can be 0 or negative. So for all pairings, this is less or equal to 0, and equal to 0, it is only exactly if pi is non-crossing. Good. Okay, but then of course we can take the limit of this, so we can consider our random matrices going to infinity, the size of them going to infinity, and then the moments of this converge to the moments of the semicircle. So this means that actually we have a realization of a semicircle by random matrices. We can say that n by n random Gaussian random matrices converge in distribution to the semicircle n. So that we record this as a corollary of this theorem which we had before and of this observation. And this corollary is, I mean, the most basic theorem in random matrix theory, and this was done by Wigner. So this is usually called Wigner semicircle. And this was around 1955. So Wigner did not, in the beginning, consider a Gaussian unitary matrix but others. I mean, you also have convergence to the semicircle for other input distributions for the entries. Okay, so, but the proof is more or less close to say like this. Okay, so in principle, you can say Wigner proof is around 1955 or okay, so what is the statement? So now we consider not only a random matrix for fixed n, but we do it for all n's. Also for each n, for capital N, we consider a n, and this should be a Gaussian unitary random matrix of size n. And then we know for each n we know the moment, and now we just look what happens if n goes to infinity. Then we have for each m, each moment we want to look at. So we just take the limit of this formula, limit of phi of an dm. And now I'm putting the index n here to indicate that this is really n by n matrix. And then I'm setting n to infinity. And this is given by, okay, what happens here? Now, of course, I mean, I'm still summing over the pi's, and then the contribution is n to this guy here, but this for crossing pairings is 0, so the contribution of those guys disappears in the limit. If pi is non-crossing, then this exponent is 1, is 0, and then I have n to the 0, which is 1. This means the non-crossing pairing makes the contribution 1. So I'm summing over the non-crossing pairings, which makes the contribution 1. So I'm just counting how many non-crossing pairings I have. Non-crossing pairings of n. And of course, this is exactly the nth moment with semicircle pairing. And in the language of convergence in distribution, this means that this random variable, this an, converges to a semicircle. So this means that an converges in distribution to S. Now, where S is, of course, our standard semicircle. It has variance 1. Where S is semicircle variable or random. Okay, I mean, this here is just a notation for essentially that this, so this is the nth moment of the semicircle. Good, okay, and so we see that at least the most important distribution in free probability theory is also the most important distribution in the random matrix theory, at least the asymptotic regime. And so, I mean, random matrices are giving at least models for semicircular random variables, asymptotic. So it's always the idea random matrices. I mean, if they tell us something about free probability theory, we have to go with n to infinity. For finite n, the formulas are complicated. We're summing over all pairings, we have weights. Okay, that's complicated. What is easy is in the limit, where we are summing over non-crossing, but pairings and the weights are equal to 1. Good, so then that's what down as a remark. And mainly the first remark which I want to make is about the notion of convergence. So what we are showing here is that we have convergence in an average sense, so we're taking the expectation. And usually in random matrix theory, you can improve this to much stronger forms of convergence, namely you usually have almost true convergence. Oh, okay. And this is, of course, this is true here, and it will also be true in other theorems, which I'm telling you, but I'm not going to talk about this, or we are not going to prove those things. Huh? But it's good to have this in mind, that actually this convergence here, which is with respect to the expectation, is even almost true convergence. And maybe later, at some point, I will show you some pictures about convergence, and then maybe we can talk a little bit more about this. But so for now, let me just write this down as a remark. So we have shown here convergence average with respect to the expectation. So this means, so what we have shown here is that for all m, we have the expectation of the trace of an to the m converges for infinity. And it converges to the corresponding moment of the semicircle. Okay, but this is telling us, I mean, a trace of an to the m, that's a classical random variable, and so we claim that this classical random variable converges to some number, the moment of the semicircle, if I take the expectation. Okay, but what is actually true is that this classical random variable converges almost surely with respect to the underlying probability measure to this number. This is much stronger. Okay. This can be shown by, for example, doing estimating the variance of this random variable. So one has to see that if I go to infinity, the variance goes to 0 fast enough. Okay, so one can define this essentially by doing variance estimates, but this has nothing to do with the limiting semicircle. This is just ordinary statements on the type of convergence. Also, I can refine this to stronger forms of convergences. And namely, what is true in this case is that the classical random variable, the trace an to the power m. So for fixed m, this is a random variable which depends on n, and then we look what happens with this random variable if n goes to infinity. And here we have seen under the expectation this converges, and by average it converges, but it also converges surely. Or in probability, I mean there are different ways of phrasing this. Okay, so I just want to point this out, so we will not go more into this. We will not consider such questions here. I mean, we are just interested that, I mean, random matrices converge somehow to the free limit, to nice objects in free probability theory. The strength of this convergence is not what I want to do this here. Okay, so we will not consider such questions here, but I want to point out that this strong convergence is not only true in this Wigner semicircle law, but also in the theorems which I will show you later today and next week. Okay, so such stronger versions convergence are usually true for further results which we will bring. Good, okay, but now that the main concern now is not strengthening the form of convergence, but trying to get more results of this type, where we also see the real force of free probability theory in freeness. So we only see one distribution. Okay, and the semicircle, okay, it's important in free probability theory, but a priori this doesn't tell us that freeness is there in the random matrix world. Okay, but actually, when Wojnarowski observed, of course, after proving the central limit theorem, it was clear the semicircle is the important distribution free probability theory, and this Wigner semicircle law, this was much before, 1955. This was 30 years before Wojnarowski started free probability theory. Okay, and of course, he was aware of this theorem, and so at least this points to a direction between the subjects. Okay, so it's not clear whether there's more than this, but Wojnarowski could show that actually there's much more. So namely, we can also find freeness itself in random matrices. Okay, so occurrence of the semicircle as basic distribution for random matrices hints at least at the relation between the world of random matrices and the world of free probability. Okay, good. But of course, in free probability theory, the main thing is not just look on one random variable, but on looking on several of them, and then between them, the notion of freeness is the important thing. And so, Wojnarowski would show that actually, also in the random matrix world, we get an asymptotic version of freeness. So, Wojnarowski is concrete, this idea that there might be more relation between free probability and random matrices. By showing that also freeness itself shows up in the random matrix world, and as before, it shows up asymptotically. If the size of some matrix goes to infinity, shows up asymptotically in the random matrix world. Okay, so now I want to present you this. There are several theorems in this direction, and I want to present you the first step, the basic theorem in this direction, where instead of just one Gaussian random matrix, we consider several of them. And of course, we have to choose the classical joint distribution between them, and then we just take independent copies. So we just take the most canonical thing which we can do. If I want to have to consider several Gaussian random matrices, I just take them independently. And then I want to see what happens with their joint distribution. Okay, so let me formulate this here. So this is the basic theorem for the lesson. And this was around 1991. So maybe this was 5 or even more years later after free probability theory was invented. So it took a while to find this relation. Okay, so now we consider not only one Gaussian random matrix, but let's say q of them. And again, for each n, for each size, we have one of them, so we let n. So we consider an1 up to anq. So those are q matrices. Each of them is a GUE of size n, and I have q independent ones of them. So this consider this, and for each this should be q independent GUEs. Okay. Independent, of course, means that the entries of the different random matrices are independent. The entries of such a guy are classical random variables. And so I have entries for the first one, I have entries for the second one, and And I mean, I know how the entries for the first one behave. They are GUVs. Most of them are independent up to the symmetry. For the second one, the same. But now I also have to specify what is the relation between the entries of the first and the second one. And I say they are independent. Oh, that's what I mean here is independent. So all the entries among the random matrices here are independent. Okay, and then we have the analog of this statement, namely that now, so each of them, I mean each of the A's here, of course, converges to a semicircle. But now, of course, we have Q semicircles in the limit, and now the joint distribution of the random matrices should also have a joint distribution in the limit. And of course, I mean, if things are nice, what do we expect? We expect that in the limit, the semicirculars are free. And that's indeed the case. So the statement here is then we have for n equal to infinity, now that the joint distribution between those Q Gaussian random matrices converges in distribution to corresponding Q tuple of free semicirculars. Which means, of course, that any joint moment here converges to the corresponding joint moment of free semicirculars. So I mean, the S's here are free semicirculars. Okay, so I need a little bit more space to finish the theorem. Maybe I erase this here. Just saying what the S are, and actually that what we are seeing here is what we usually then say is asymptotic freeness between those guys. They converge to something which in the limit is free. Okay, so we say in distribution, this Q tuple of the independent Gaussian random matrices converges to this tuple of S1 up to SQ, where this S1 up to SQ are free semicircular variables. Actually, variables 1. The main point here is that they are free. Okay, and so this means in particular that the tuple of the Gaussian random matrices, they are asymptotically free. That's more or less just, I mean, what I mean with the notation asymptotically free. Asymptotically free means they converge to something which is free. So, okay, so let us prove this, and actually the proof is more or less the same as the proof which we did in the case of one Gaussian random matrix. We only have to put this extra index here. So before we only had one AN, and now I have Q of them, and I have an index here. And this index, I can put it more or less at everything appearing in my proof, and most of the arguments are not affected by this index. So let us look at this again. So that's somewhat a nice thing of those moment calculations. The proof, if you only have one variable, and if you have several variables, very often is the same. Because you have, of course, you have an additional index which tells you which variable you have, but for many arguments, it doesn't really play a role which variable this index has. Of course, at some point, it must tell us something about the freeness of the limit. So of course, it tells you at some point, but the basic arguments are more or less the same. So let us prove. So we have now our matrices. These matrices A and N. And because I calculate traces and all those things in terms of the entries, so I should give names to the entries. Of course, I call them A, I, J. But now I also have here this index, let's say R, and I also should put an index R in here. Okay, so I have Q different this. So this is an n by n matrix. Okay, and I'm not putting index n here, because okay, there is only so much space for putting indices. It's clear this also depends on n. No? But again, the calculation is for fixed n, and then we get a final result, and then we send n to infinity. Good. Okay, and now of course, as in the case for one random matrix, the main point is to specify the joint distribution of all those entries. Okay, but as I already said, what we have here in each of those guys is a Gaussian family, but if I take them all together, it's still a Gaussian family, because what I have here essentially is a collection of independent Gaussian random variables. This forms a Gaussian family, and a Gaussian family is determined by specifying the covariance, because then all the higher moments are calculated out of the second moment. Okay, so what is now our assumption about the covariance of those guys? So, assumption on our Gaussian random matrices says that if I take all those entries together, so I take the A and J, I take the I and J entry of the Rth matrix, but I'm running all the matrices, and I'm running all the entries. They together form a Gaussian family. And I have to specify their covariance, because that's the input for my calculations. And that specifies all the joint moments of all those guys. Also, I have to say what is the expectation of, let's say, the IJ entry of the Rth matrix and the KL entry of the P matrix. Okay, what is this? So first of all, different matrices are independent. So if R is different from P, then this is zero. Because then I have here a product of independent Gaussian guys, and then they are centered, each of them, so this is zero. So this means this I and P gives me the condition that I have the delta of I and P. Okay, and if R is equal to P, then I just have one Gaussian random matrix, and then it's the same as before. I mean, then I need the symmetry condition, so this here has to be the adjoint of this here. So this means this index must be the same like this, and this index must be the same like this. So I need that I is equal to L, and I need that J is equal to K. And only if all those things are satisfied, then this is not zero, and if it is not zero, then it's 1 over N, because that's our normalization. Okay, and you see this is the same as before, only we have in addition this I and P, but this only gives us this delta function, saying that those indices also must be the same. Okay, now we can do the calculation from last time, looking on a joint moment. So I want to calculate now, okay, nth moment, so I multiply m of my matrices, but now of course it can be different for matrices. So let's say I multiply the P1 matrix up to the Pn. So I'm using a multi-index P to indicate which matrices I multiply. Okay, so what is this? So this phi is of course taking the trace and taking the expectation. The trace is the normalized trace, so I'm getting the factor 1 over n. And then I do the matrix multiplication and the trace, which gives me all those summations over the indices. So I have here my couple of indices running from, so I have I1 up to Im. 1 and capital N, so I write this as a function from 1 to 2m to this. Okay, and then I take the expectation, and what do I have here? I have here, of course, I have the matrix product of those matrices here, so I1, 2, 3, up to M. Okay, so this here is matrix multiplication, summing over those indices, and this is the same as this is the same as the next one, and then I'm also taking the trace, which means this is the same as this, and I'm summing over this index. And of course now, they are coming from different indices, so we also get the index here. So I have to put here 1, 2, good. Okay, and now we're doing the same as before. I have here the moment of a Gaussian family, a product of elements from a Gaussian family. So the Wick formula tells me how I can write this in terms of the second moment. So here, so I have this 1 over n. Then I have the sum over I indices. And now I have for each fixed I1, I2 and so on, I have here a moment, the nth moment in this A's, and I use the Wick formula. The Wick formula tells me for such a moment I should sum over all pairings of M. Of course M should be even, otherwise this is 0 anyhow. So I'm summing over all pairings of M elements, and each pairing makes a contribution. And this contribution is given by the product of contributions coming from the blocks. Each block corresponds to a second moment. This makes a contribution. So what I get here is the product of the blocks of I. Let's say I take the block RS, and then I get the product of the corresponding second moments, where I take the variables corresponding to all blocks. So if I have the block RS, then I take the second moment of the variables sitting at the position R and sitting at the position S. What is this here? So you see, I mean, the I indices at the position R is IR and IR plus 1. The same for S, IS plus 1. And now I have addition this P index, but this is just here I have position R, so here I have P of R, and here I have P of S. Okay, so that's the second moment, and for the second moment we have specified the distribution by this formula here. So now it's again just a couple of delta conditions. If it is different from 0, then it will be 1 over n. So this is here 1 over n. But in many cases it will be 0, so maybe I have these conditions. So I need that this, for the i's, I need that this is equal to this, and I need that this is equal to this. So those two conditions. So I need that delta I of R should be the same as I of S plus 1, and here the same delta of I plus 1 should be the same as IS. And then I get the additional delta condition on the indices P, and this just tells me that this P of R should be the same as P of S. Delta P of R, P of S should be the same. And you see here, we're doing the same calculation as before, but now we have just this additional contribution for the P's. But this is just this delta value. This is quite easy to control. And of course we are doing now the same as before. So what we are doing is we exchange the summation over the i's and the summation over the pi's. And of course here we see this product of the pi's over all blocks. For a block, we get two delta contribution. One contribution which is about R, it tells us that I of R is the same as S is P of R, and the effect of this plus 1 is the gamma. That was the reason that we introduced the gamma. So what I have here is actually, this is pi of r gamma of this. And here, the same way, this here is pi of s gamma of this. So the contribution for the two elements in the block are just that I of this element is the same as I of gamma pi of this element. Okay, so this means what I have here actually is the product for each number 1 up to n of this delta function. Okay, and then we exchange the summation. So this means the first sum of all the i's. And then I'm summing over the i's. But for the i's I have this delta conditions, and this condition tells me that the I must be constant on the orbits of the gamma pi, the same as before. Okay, so this means I'm just getting a contribution. I have the freedom of choosing a value for I on each orbit of gamma of pi. This gives me this n to the power of the number of orbits, number of cycles of gamma pi. Then I have this 1 over n from here, which is minus 1, and I have this 1 over n for each of the blocks in pi. I have m over 2 blocks, so I have here m minus 2. So that was the same as we did before, but now in addition I also have this delta contribution. So what does this tell me? This tells me actually that if I have a pairing, then the pairs of this pairing must connect the same p-value. So for each pair in my pairing, p of r and p of s must be the same. R and s are the two positions which are connected by my pairing. And this then tells me actually that I'm summing here not over all pairings, but only pairings which satisfy this constraint, and this constraint is nothing else than pi is less or equal to the kernel of pi, of p. So we had this notation. P was a multi-index, or alternatively a function like this, and the kernel of this p is the partition which tells me whether indices are the same and whether they are different. A block corresponds to positions where indices are the same. So on each block they are the same. And if pi is less than this tells me exactly that pi must connect the same p's, the same values of p. Good. Okay, so you see we get our calculation of this joint moment goes in the same way as before, and the only difference is that we now get this additional condition that in the summation over pi we are not summing over all of them, but only over pi which respect this p, which means I'm only connecting the same matrices with each other in my pairings. Good, and again, now I can send n to infinity, and this here, the p has nothing to do with n. So I mean, again, n going to infinity just is about what happens with this, and this is the same as before. Sending n to infinity just means that instead of summing over all pairings, I'm summing over non-closing pairings. And then we get a formula which we should recognize as the formula for the moments of free semicircles. Because that's what we are claiming. We're claiming the limit, we are getting the formula, or we get in the moment, the corresponding moment of free semicircles. Yeah, this is quite straightforward. So this is the first asymptotically. Taking the limit of my moment, the moment which I am considering is this moment of the product of my Gaussian random matrices, indexed by the p's. One matrix, the M matrix, that is in the limit, is given by this formula. n goes to infinity, I get here contribution 1. If pi is a non-crossing partition, then I get a contribution 0 if pi is a crossing partition. So what I get is that I'm summing only over ones. I'm summing over non-crossing partitions, but of course I still have this condition that pi has to be less than the kernel of p. Okay, before we had all the p's were the same, we didn't have this, and this was just the nth moment of the semicircle. But now, of course, what I have here is the moment of corresponding product of three semicircles. Because this is essentially, you can also see this as the moment cumulant formula for this product. No? So you can say this is the same as summing over pi is in non-crossing partitions, let's say, and I take kappa pi of my semicirculars, the first up to the two guys. So I'm replacing my Gaussian random variables by the corresponding semicircular element, and I'm saying what I have here is the same as doing this here. So taking the cumulant of those guys. So why is this? Because this contribution here gives me exactly the ones when I want to have it, and 0 otherwise. Because this is a cumulant of three semicirculars, and of course cumulant. So those are three semicirculars. So they are in particular semicirculars, and such a cumulant is a product of cumulants for gases, and because I have a semicircular, only the second cumulant is different from 0. So this means that this kappa pi is different from 0. This means the blocks of pi must all be pairs. So that I only have second cumulants. This means I have here a 1, only pi is a pairing. But of course, furthermore, this pairing should only connect the same S's, because they are free. Mixed cumulants vanish. So this means I shouldn't have a pairing which connects an S1 with an S2. I only should connect the same variables here, which means pi must be less than the kernel of theta. Okay. If those guys are not satisfied, then such a cumulant is okay. So this means this here is exactly 1 under those conditions I have here. Okay, so I just have written this 1 in this form, and now what I have here, of course, is the moment cumulant formula for the moment of these guys. This here is nothing else than phi of the product of those guys. That's P1 minus S1. So you see, asymptotically, the moments, the joint moment of my independent Gaussian random variables converges to the corresponding moment in my three semicirculars. And somehow you see that how you get these conditions which correspond. Semicircular correspond to pairings, and freeness corresponds to the vanishing of mixed cumulants, which means here in this moment we only also have pairings which connect the same matrices, not different ones. Good. Okay, so this is the proof of this statement. And this is, from our point of view, a big step. I mean, the proof is more or less the same as for the semicircle statement, but it's really, the meaning of this is really, you really see the notion of freeness in random matrices. So it's, in a sense, this really is a very important theorem. Good. Okay, but on the other hand, of course, it's a theorem which still is quite special. So we find free variables among random matrices, but these variables have a very special distribution. They are just semicircular. So with this, we can only realize free semicircular distributions via random matrices. And this, of course, is very special. And the hope is, of course, that we can go further. The idea is, of course, that we should in the end be able to realize all free distributions by asymptotically by random matrices. Okay, and so now the next step in this direction. And you can do this by replacing at least one of the distributions here by something arbitrary. Because this means we have to go away from Gaussian random matrices. Gaussian random matrices give us semicirculars, so we should try to include also other matrices. Yeah.
So that multi-index P is from M to Q?
Yeah. Here, P1 up to Pm, I mean, this takes on values between 1 and Q. No? Okay, this just tells me that I take here a product of any of my matrices which are. Okay. But Q could be 2, let's say 2, then I only would have 2 Gaussian random matrices, and they converge to 2 free semicirculars. Okay, and now I'm saying, okay, one of the 2 you could replace by something else, and still you get freeness. So let us mark this. The first what do we see here? So this shows that we can model 2 free semicirculars by random matrices. Let's say 2. Of course, we can also use Q, but let's say 2 free semicirculars asymptotically by independent independent Gaussian random matrices. Good. Okay. So this is quite some step because we have freeness. But on the other hand, it's still very special because you can only model semicircular distributions. Okay, the question is, can we go over to some more general distributions? So the question is, can we also model other distributions? Okay, and we can do this. Out. Talk about this in the following. So it turns out that actually we can, in this context, we can replace one of the 2 Gaussian random matrices by, let's say, an arbitrary matrix. So the reason that we get asymptotic freeness here is not that we have 2 GOEs, but actually it's enough to have one of them a GOE, and the other can be more or less anything. Okay, so it turns out that replace one of the Gaussian random matrices by any matrix, and let's say we're given by a deterministic one, so we don't need randomness there, a deterministic matrix, and for this we can asymptotically prescribe any distribution. Good. Okay, so that's what we are going to do. But maybe first, what do I mean with a deterministic matrix? I mean, I'm talking about random matrices, and this means, of course, I have matrices where the entries are, classical random variables. Okay, I mean, of course, a deterministic random variable is just an ordinary number. So where randomness doesn't play a role. So this means a deterministic matrix, or deterministic random matrix, is just an ordinary matrix, which of course I can consider as embedded into my random matrix space of random matrices. Also, it's just a constant. Okay, so and then of course if I calculate the moment of this, I'm just using the ordinary trace because the expectation doesn't do anything there. So deterministic matrices are in a sense constant random matrices they are just matrices. Usually I denote them, let's say, by D. So they are n by n matrices, just ordinary n by n matrices, which of course I can consider as sitting in my space of random matrices. I mean, the random matrices are n by n matrices, where the entries are infinity functions on my underlying probability space. So I mean, here I have entries. You can also say the entries are random functions, but they are constant random functions. Okay, so those are very special ones. So these are just ordinary matrices. But embedded in our space of random matrices. Embedded in all these algebras, algebra. Of random matrices. And of course the state, which I use on my star probability space of random matrices, state phi, this is the trace tensor E. Of course there is just by taking the trace, because the expectation doesn't do anything. So, those is just given by taking the trace, and of course the trace which we use is always the normalized trace, no? By taking normalized trace. So the phi of such a deterministic matrix is just the normalized trace. Good. Okay, so now what we want to do is we want to take now Gaussian random matrices, but replace one of them by a deterministic matrix. Okay, well let's say we take as before, maybe Q, or maybe I call it T, the following. I take T, independent Gaussian random matrix, and then in addition I take a deterministic matrix. And then we want to see, actually we are claiming, and then also this deterministic matrix becomes free in the limit of the Gaussian ones. And this means we have again to calculate mixed moments in the Gaussian matrices, but also including these. Mixed moments in the A's and D's. Okay, and again we can do a formulation. We can do this calculation for fixed n, and we get a formula which is again conceptually nice and which we can control if n goes to 3. Good. So let me write down this formula and then do the proof. And of course it will be somehow split as before, but of course it will become a bit more complicated because now the D's are also shown. Our GOEs will be the same. For the GOEs, the description will be like this. I think I can erase it. If we need it, we will remember. Oh, this I will remind you. Okay, so let me write down the statement. And again, this is due to Wigner. I mean, all this was in this 1991. He also included those deterministic. But I think actually in the beginning he only had diagonal deterministic. It took a while before it became clear that one can also do this. But we do it right away this time. So here's the theorem. So what we consider independent GEs. Now I say T of them. So this should be T independent GUM. And at the moment n is fixed. We just do the calculation of the moment for this specific environment. And then in the next step we send n to infinity. So n is fixed here. So we have those t-dependent n by n Gaussian random matrices. But then in addition I also have just an n by n matrix, a deterministic one. So I call it D. This is just an ordinary n by n matrix, which I consider now as a deterministic matrix. Okay, and then I want to calculate mixed moments in the A's, but now also the D's must be involved. So I should consider any product in the A's and the D's, and the A's of course need their parameters. Okay, so then I have to look on the possibilities. So then we have, let's say again I want to multiply the number of them, which is given by then I also number Q1 up to Qm, which are natural numbers, possibly also 0, and all the p's, I mean the p's as before, indicate my A matrices. So I have T1, Tm, this is between 1 and T. And so what am I looking at? I should look on products of the A's and the D's. Okay. And of course, I mean, let me write it down. So what I'm looking at is I'm taking an A matrix P1, and then I'm taking the D matrix, but possibly a power. So this is now really a power of my D matrix. This is just the index. Okay. Then I take another A matrix, P2, and another D matrix. Okay, there's only one D matrix, but another power of this, and so on, up to a M, D, Q. And this gives me all mixed moments in the A's and the T's. Because you see, I allow also for the Q, I allow 0, which means the D's here might be absent, and then I just have a product of A's. Of course, I mean, what I should consider is some product of A's, then somewhere in D, other products of A, another D, and so on. Okay, but I want to write it in this form, because this looks more like an alternating thing in a couple of things. And we have some knowledge about if I look on such guys and free variables. Okay, but I mean by choosing all the P's and the Q's, this contains all information about all the joint moments in the A's and the T's. Good. Okay, and the claim is that we really can calculate this, and again it's given at the same time a formula as before, so namely we are summing over pairings of m elements, so essentially we are now summing over pairings of the A's. I mean, if you recall, we have a formula if you have an alternating product of three variables. So I have A, B, A, B, A, B, and I want to calculate the moment of this. I should sum somehow over the cumulants or the parent or the partition of one of them. This goes with the cumulants, and for the rest I get something else. So this means it's good to have something where I do still the parent of the A's. And again, I should respect the P index as before, so I want to sum over the pairing where I have which are less than the kernel. Then I get the same contribution in n as before, the number of gamma pi minus 1 minus n over 2. But now, of course, I should also get a contribution for the D's. I mean, before you could say all the D's are equal to 1 or the Q's are equal to 0. So I just get the product of the A's. And then that would be this formula. Okay, but now I have some D's in between, so there must be some contribution of the D's. And actually, what we get is that I have here, of course, a trace. Actually, I get a product of traces, and this product is a product along pi gamma or gamma pi applied to the D matrices which I have. So applied to D Q1, comma D Q2, applied to Qn. Okay, and this notation is our usual notation. I mean, we have a notation that if I have here a linear function or whatever, and I index it, usually I index it by partitions. And then this is the product of this function corresponding to the block decomposition. Okay, and here, I mean, here of course, this is now a permutation, but of course I can use the same notation for permutations, where I multiply along the cycles of the permutation. So this means this notation here so there I have trace, and here I have permutation sigma, let's say, and I apply this to, let's say, some matrices, d1 up to dn, let's say. So sigma is here permutation in Sn, and d1 up to dn, n by n, just ordinary n by n matrices. Then this here is the product according to the cycles of sigma. These are the cycles. Usually we had here partitions, then I was doing it for blocks, but here I'm doing it for the cycles. And then for each cycle I take the trace of the elements which correspond to this cycle. The ones which show up here at the position where my cycles are. So I mean, we know this maybe as before, we went up to the n, but restricted to the cycle C. So this here is the product of these along the cycle. Okay, this is the same as for our partitions. Maybe the only problem, maybe the only thing to think about is that a cycle usually has no beginning and no end. I mean, if I have a block of partition, I can say I really have a beginning and an end as I write it down, and then of course I multiply in this order. The cycle, I mean, the cycle goes just round, so there's no beginning and no end, so it might not be clear how I should multiply those guys. But because I'm taking a trace, the trace has this cyclic symmetry. This means I don't need a beginning and an end. I can multiply, I can just start somewhere and then multiply in a cyclic way, and it doesn't matter if I start at some other place. Okay. So at least for traces, this is well defined also for permutations. And that's what I mean. Okay, good. And so you see, we have again a very similar formula. Up to here it's the same, and we just have to see where do we get this from. But again, the point is really the d's, we can de-risk them in a very concrete, precise way. We really can control the contribution if I put in some d's in between. Good. Okay, so let us do the proof. And of course, it's now a lot of indices and trying to see how they fit together. The point of the proof again is to do it in the right way, the right notation, and putting things together in the right way, and then it just comes out automatically. No? If you do it in the wrong way, then it can be really a mess. Good. Okay, so let us prove this. Here. Here. Okay, and of course, so we have our A matrices, we have the D matrices, we should give names to the entries. So I write, of course, AP, I write the J, and I put the P here, and maybe I'm not putting it in a bracket now. I mean, this is really a super index, not a power in this case. Okay, so this is my N matrix. Then I have the D's, and actually I mean I have the powers of the D's. Huh? So various places I have different powers. So I have D to the Q, and you know this by D, I, J, and here I'm also putting the Q there. Of course, this is now again just the index. This is not the power of the Dij. I should put brackets there. I mean, there will be so many brackets. I hope it's clear. So I denote this by this. And of course, with these here, I mean, in principle, they don't have, for this formula, they don't have to be the power of 1D. It could just be different constant matrices. So you could also say that this is not the power of D, but this is just some of, you also have Q different, or you have different ones. Okay, which I denote by this. Good. Okay, and then we have to calculate. So what do we have to calculate? And so we have to look on this mixed moment. So I have A1, let me see. Then we write what we want to calculate, let me write it here, and then I continue there. It's good to have a lot of space for this. So phi of A, P1, and Q1, and so on. A to the PM, D to the QM. So that's the moment that you want to calculate. Now I'm writing it down, what this means in terms of the entries. So what is this? So the phi is taking the expectation and the trace. The trace is the normalized trace. So we have this one on my n. And then I have now to do matrix multiplication between all these matrices, and I have to take the trace. So I have to sum over a lot of indices. And here, I mean, here I have a product of 2m guys. So it's not only that I need m indices, but I need 2m. And some of them I call I, some of them I call j. So I'm summing here over I1 up to In, but I want to sum over j from I1 up to n. Okay, so I take the expectation of, so first I have to matrix A, and there I denote the indices by I1 and J1. Okay. Then I multiply this with the D matrix, so I have now D, and so here I have now, because I need matrix multiplication means that this is the same as this, so I have here J1, and the next I call I2. So then now again I get A matrix, and then I have here I2, I3. Yeah, I2 and the next is J2. So you see I'm calling the indices of the A's, I call I and J. And for the D I have the J and the I, but in a different way. Okay, and so on. The last one is A of IM, JM, and D of JM. Okay, and then because I have a trace, I have to go back to the first index, which was the I1. This is okay. And now, of course, all those A's and D's also have their upper indices, telling me which of the A's and which power of the D I'm considering. So here I have the P1, P2, PM for the A's, and for the D's I have the Q. So this is Q1, Qn. But again, this upper index is not so important. I mean, the main action appears on these indices, the matrix multiplication is done. Good. Okay, so now you see I have here a product of things, of the A's and the D's. And I take the expectation of this. But the D's are, of course, deterministic, so I just can't take them out. The expectation doesn't do anything on them, so I can split this, of course. I mean, the A's and the D's are just numbers. Everything commutes. Of course, I mean, where they are coming from is encoded in the indices. So I can write this just as the product of the A's times the product of the D's, and the product of the D's I can take out of the expectation, because the D's are deterministic. So, yeah, so this whole thing here, I'm writing now as the expectation of the product of the A's. So I'm just connecting the A's. I have AI1, J1, AI2, J2, up to AI Jn, and the corresponding P's there. And for the D's, I just have now the product of the D's. So I have D, J1, I2, D, okay, next would be J2, I3, up to D, Jn, this one. So you see here, the A's I just have I of some index times J of the same index. The D's, it's mixed the other way around. I have the J, and then I have I of the following index. Okay, so that's just how I've denoted guys by I and J. Good, so we have this, and okay, of course here it's now just again where I can use the big formula, because the A's are forming our usual Gaussian family. And of course there we know what to do, and then we have to see how to deal with the D's. But for the D's, let me see. Let me see again. Yeah, so this here, we use our big formula. So this means, still for fixed I and J, we get here just the sum over all pairings, pairing of n elements. It's just the pairings applied to the A's. Okay, and what is the contribution? Contribution again is the product over the blocks, S, I, and then I should take the second moment of the variables which are sitting at position R and the position S. And let me see what this is. Maybe here I should now put also maybe this index which tells me which matrix I consider. But this is just a P of n. So you see that for the A's, the indices are quite nice. I mean, the first guy has all the ones, the second has all the twos. So you're mixing up P's and D's. I mean, this and this is not the same. So, but here the notation is chosen in such a way that the level of the A somehow things are very nice. Okay, so this means I have to take the variable at position R, which of course is then A of IR, JR, is the upper index PR, and one at position S is A of IS, JS, PS. Okay. This is now the second moment. This is prescribed in our theorem by saying that and this is only different from 0. If this index is the same as this index is the same as this, and also this must be the same as this, because the matrices are independent. And if it is different from 0, it's 1 to 1. And so we get here delta. This tells me that I of R is equal to J of S. This here tells me that J of R is equal to I of S, and then I have again this condition which tells me that the P indices in this pair must also be the same. They only take pairings which connect the same P's, which means I get again here this condition. Actually, I'm only summing over pi's which are less than the kernel. Okay. Yeah, so, and maybe again, on the level of the D's, of course we should write things in terms of our permutation, of our pairing. So I have here, we have here the shift of the indices. I have here J of 1, but I of 2, and of course the 2 is one more than this. This is actually the application of this gamma. That was the gamma was always coming in because at some point I'm adding a 1 to my index. And that's what's happening here. So this I of 2 actually is I of gamma of 1. So gamma of this I of 3 is I of gamma of 2. And this last guy here is I of gamma of n. So again, we can say I have here indices which correspond to the position, but here I have to use this gamma. Okay, and so yeah. Now we see again we do the exchange. We exchanging the summation over the indices and the summation of the pairings, and then for a fixed pairing, I have here some conditions, and the conditions tell me here that what do they tell me? They tell me actually that the I indices and the J indices actually must be the same. So this here tells me that if I have a pair, then the J index of one guy, the pair, must be the I index of the other guy. And this here is telling me the same. So this tells me that actually all the J indices are the same as some I indices. So if I'm fixing my I, the J's are fixed. I don't have a freedom anymore. So this means I can replace here the J indices, or maybe let's say better the I indices by the J indices. So what I'm doing is let's say the n term, I have here n, I have 1, and then I get a 1 over n for each pair. So I have here n over 2 once. Okay. Then I do first my sum over pairings. This is this sum, but this delta condition tells me that actually such a contribution is 0 unless pi respects the kernel of P, which means it only connects the same A matrices. So this summation here is actually only running over pi's, which are less than the kernel of P. And then this delta condition is taken care of. I can't forget about this. Okay, and then I'm summing. Now I would sum over. I would sum over J and I, but actually I have the delta conditions which tell me that if I'm fixing the J, then the I's are determined. So effectively I'm only summing over the J's, and I can express the I's in terms of the J's. So I'm summing here only over the J's. And then I'm just left with the product of the D's, but now I have to plug in the right indices. Okay, so I have D, so I have J1, okay, J1 is still J1, but the I now is replaced by a J. So the I of something is actually the J of my pi applied to this something. So you see here, the J is the same as the I of the other element in the pair. The other element in the pair is just a pi applied to this, if I consider pi as a permutation. So I have here J of pi of the index which I have there, and this was gamma of 1. Okay, then I have D, J2, and here again I have now the I index is the same as the J index, but I have to apply pi on the index which I have there, which was gamma of 2. And so on, up to the end, D of Jm, J of pi. And again, you see how I get this permutation pi gamma, or gamma pi into the game. But now it appears somehow not directly by just counting things, but really in the indices here of the D's. Okay. And of course, I mean, the D's here I also have upper indices. So I have here Q1, Q2, and Q1. Now you see, I mean, I have just the index 1 for the first guy, the index 2 for the second one, and so on. And here it's also nice. For J it's also nice, but here I have this calculation by this pi gamma. Good, and so now you see what I'm doing is I'm summing here over J, over D's, and this D, I mean, they look somehow like matrix multiplication, but it's not that. So you see I have a J index here, then I have some J index here, and this J index for matrix multiplication should appear here again, but now of course things are changed without the pi, it would appear here, but with the pi it is somewhere else, but this means it appears somewhere else, and then actually I'm doing a kind of matrix multiplication along the cycles of this guy. So what we should now observe is that this sum, and this looks like a complicated sum. When I have my entries of these D matrices, I have some indices here which look a little bit strange, and I'm summing over these indices. But I'm saying actually this is not really much more than taking the trace of power, but actually I have to do this along each of the cycles. So I'm claiming, so now you should note that for, let's say, sigma in Sm, so I mean I call pi gamma now sigma, so this is now a general statement about such a thing. If I'm summing over J indices, and I have D, I have here J1, and then I have here J of sigma 1, E J2, J of sigma 2, and so on, up to D Jm, J of sigma m. So I'm writing down the same as here, just calling pi gamma sigma. And I also have, let's say, Q1, Q2, some other indices here. That this actually is the same as taking the ordinary trace, or the normalized one, but ordinary, along the cycles of sigma at those matrices. Q1, Q2. So this means I'm multiplying the matrices which are showing up here, not just multiplying all of them, but just multiplying the ones which correspond to a cycle, and then I take the trace of them, and then I'm doing the same for all cycles, and so this means I get a product of traces, one trace for each of the cycle. Okay. Maybe I'm doing an example that this maybe becomes clear now, but this is really this is the statement. But I can do the example here. Let me take an example. Let's say sigma. So this is a permutation. Let's say it's a permutation 1, 4, 6. Let's say 2, 5, and 3. So let's see. 1, 2, 3, 4, 5, 6. So this is a permutation of 6 elements. Okay, and now, so the quantity which I have there, so I have D, J1, and then I have J, but now I'm taking this at a position sigma 1. So sigma of 1 is 4. So I have here J of 4. The next one, I have D J of 2, but now I'm taking J, the next one is sigma of 2. Sigma of 2 is 5. Then I have here J of 3, but now I'm taking J of sigma of 3. 3 is a fixed point, so I have here again J3. I have the D of J4. I take the sigma of 4, which is 6. J of 6. Then I have the J5. And I take the sigma of 5, which is 2. J2. And I have the D of J6. And I take the sigma of 6, which is 1. Okay, that's what I'm doing here, and I'm summing over all J's. I mean, all the J's are running from, I mean, I have have 6 of them. They are running between 1 and 10. Okay, but now you see, I mean, I have here kind of the matrix multiplication, but not for neighbors. Also, you see I have J1, then I have J4, but this J4 appears here again, and then I go continue with J6. The J6 appears here again, and I have the J1, and this brings me back to here. And those are exactly the quantities which contain J1, J4, and J6. And so if I'm summing now over J1, J4, and J6, I get the product of those 3 matrices, and I'm taking trace of them. So this means I'm getting this 1, 4, and 6 is exactly this cycle. So for this cycle, I'm just taking the trace of, and I mean I should put indices here to really see what I have. So I take the trace of D1, D4, D6 by doing the summation over J1, J4, and J6. Okay, and then I'm left. What else do I have? Here, for example, I have J3, J3. The J3 only shows up here. I can sum over this, and this is just a trace of this matrix. So I have a trace of D3 corresponding to this cycle. Then the summation over J3 is also done. And then I'm still left with summing over J2 and J5, and you see I have J2, I have J5, and the J5 appears again here, and then I continue with J2, which is this here. So this is just a trace of this matrix and this matrix. Trace of that's along this cycle. Okay. So I get exactly what I'm claiming there. And I hope this also makes now really clear what I mean with this notation. So I mean this here is now forming a trace along sigma of D1 up to D6. I'm taking the product of the traces along the cycle. And you see I have here the cycle 1, 4, 6. But of course it might not be so clear that I should start at 1 or 4. But this is the same as D4, D6, D1. So in the cycle, I could also write this 4, 6, 1. It's the same. Good, okay, so this means, yeah, I'm really getting this here. And of course, I have here the product of the unnormalized traces, and the quantities which are our moments are the normalized traces. So I should rewrite this in terms of the normalized trace, and the difference between normalized and unnormalized trace is always a factor 1 over n. So this means that this here, if I want to write this in terms of the little tr, I get the same expression. Of course, for each factor in the capital trace I have here, I have to multiply this with factor n. So I get here the factor n, and how often? As many cycles as I have here, because I mean I have for each cycle I have a trace. So I get the number of cycles of sigma. Okay. So this means this complicated looking sum in our formula for the calculation of the mixed moments actually is just of this form. I really can do this summation, and it really gives me something which corresponds to the moment my matrix is D. That's the information which I want to use about my matrices. So this means here I can now continue. So what I actually have here is sum over my pi's. So I'm summing over pi's, which I repeat 2 of them, but which respect kernel of p. And then this whole sum here is just given by taking this trace, but now of course what I call here sigma is pi gamma of Q1 of the matrix is appearing here. Those are the powers of D. dq dq1, dqm. Okay, and then I also get this factor n. And I also have some factors of n coming from here. And you see, those are the usual factors which we had before. So I'm going to have n. So I get here the number of cycles of sigma. So I take the number of cycles of pi gamma. Usually we had gamma pi before, but the number of cycles is the same. So I can also write this as the number of cycles of gamma pi. And then I also have this 1 from the normalization of the trace and this m over 2 from the covariance of our entries. Minus 1 minus m over 2. And that was exactly what we are claiming. Okay, so you see that you really can control. That's the amazing thing. In the beginning, probably you wouldn't expect that you are able to express mixed moments in the A's and the D's in a form which actually only contains the moments of the D's in the final form. Because it might, of course, the D's contain much more information. The D's is a matrix, and we're only caring about the moments of the matrix. And it shows you are calculating mixed moments in the A's and the D's. They really depend only on the moments of the D's, not on more information about that. Okay, the fact is that in this summation here, each of the term here depends on all the indices, all the entries of the D's. But this summation really brings me back to product of traces. Okay, and you also see, what we had before was where all the D's were equal to 1. Without the D's, then of course this contribution is just 1, and you see now where this term before was just given by counting how many free indices do we have. All this also comes in this more complicated calculation. Where it comes from. Good. Okay, so we have now again a very nice formula for finite n, and then next time we just look what happens if n goes to infinity. Of course, I'm claiming that in the limit the d becomes free. Of course, I must then make the assumption that I have now a sequence of d's, of matrices, which have a limit distribution. Okay. So that this formula converges, but then the point is that actually it converges to the formula, which is a formula for free variables. Okay, but this is also quite straightforward. The main logic is done. So next time I will talk about this. Okay, that's it for today.